Hi, myself Dr. Vindra Kumar. Today in this session, we are going to discuss about the divide and conquer techniques. You will learn about divide and conquer algorithms and how to determine the complexity of these algorithms. In particular, you will learn how to associate a recurrence relation with a specific divide and conquer algorithm and then solve this recurrence to find that algorithm's complexity. So first of all, we need to understand the concept of divide and conquer. A typical divide and conquer algorithm solves the problem using the following three steps: divide, conquer, and combine. The divide and conquer technique involves taking a large scale problem and dividing it into some similar sub problem of smaller scale and recursively solving each of these sub problems and conquer the problem by combining the solutions at the various level to form the overall solution to the problem. The divide and conquer algorithm works explained with this tree structure by recursively breaking down a problem into two or more sub problems of the same or related type until these become simple enough to be solved directly. As shown in the tree, the solutions of the sub-problems are then combined to give a solution to the original problem. Divide and conquer algorithm take as an input the problem P, break the given problem into sub-problems of same type. This step involves breaking the problem into smaller sub-problems. Sub-problems should represent as a part of the original problem. This step generally takes a recursive approach to divide the problem until no sub-problem is further divisible. In conquer part, recursively solve these sub-problems. This step receives a lot of smaller sub-problem to be solved. Generally at this level, the sub-problem are considered solved on their own. In last combined section, when the smaller sub-problems are solved, this stage recursively combine them until they formulate a solution of the original problem. This algorithmic approach works recursively and conquer and merge step works. So here in this algorithm, initially we have the problem P. If it's smaller enough, then we solve it. Otherwise, divide that P into a sub problems like P1 to Pk, and then again apply divide and conquer on each sub problem, and if they are solvable, then combine their solutions to create its original solution. The computational complexity of a divide and conquer algorithm can be estimated by using a mathematical formula known as a recurrence relation. If we have a problem of size n, then suppose the recursive algorithm divide the problem into a sub problems, each of size n by 2. As in binary search, initially this a is equal to 2 and b is 2, and on a second iteration the a is 2 and b become as a 4 in term of n, because initially we divide the whole array into two parts and then the sub part is again divided into the two parts, means the n is divided into 4 parts. So on second iteration this b become as a 4. Additionally, suppose that Cn represent any further computation that are needed to combine the solution of the sub problems into the overall solution of the original problem. The following are some standard algorithms that follow divide and conquer algorithm. First one is binary search. It is a searching algorithm. In each step, the algorithm compares the input element x with the value of middle element in array. If the value match, return the index of the middle. Otherwise, if x is less than the middle element, then the algorithm recurs for left side of the middle element, else recurs for the right side of the middle element. Second is quicksort. It's a sorting algorithm. The algorithm picks a pivot element, rearrange the array elements in such a way that all elements smaller than the picked pivot element move to the left side of the pivot and all greater elements move to the right side. Finally, the algorithm recursively sorts the sub-array on the left and right of the pivot element. And last example is merge sort. It's also sorting algorithm. This algorithm divides the array into two halves, recursively sort them, finally merge of two sorted halves. Thank you. Hi, myself Dr. Vinder. Today in this session, we will discuss about the binary search algorithm that come under divide and conquer technique. Binary search is an efficient algorithm for finding an item from a sorted list of items. Searching is a process of finding a particular element among a number of given elements. Any search is said to be successful or unsuccessful depending upon whether the element that is being searched is found or not. Binary search looks for a particular item by comparing the middlemost item of the collection. Binary search is very fast and efficient searching technique. This search algorithm works on the principle of divide and conquer. It requires a list to be sorted order that may be ascending or descending. In this method, to search an element, you can compare it with the present element at the center of the list. If it matches, then the search is successful. Otherwise, the list is divided into two halves. One from 0th element to the middle element, which is the center element, first half. Another from the center element to the last element, which is the second half, where all the values are greater than the center element. The searching mechanism proceeds from either of the two halves, depend upon whether the target element is greater or smaller than the central element. If the element is smaller than the central element, then the search is done in the first half, otherwise search is done in the second half. So in this algorithm, repeat this procedure until low is greater than high. If at any iteration we get a mid is equal to key, we return the value of mid. This is a position of key in the array. So in this algorithm, here we see low greater than high. When this condition becomes true, that means we have the key value. Then we return -1. If this condition is false, then we calculate the mid. If the mid of that array is equal to key, return the mid. If mid is less than the key, then again we call the binary search algorithm recursively by change the low to mid +1, and high is as it is, then key value. If mid is greater than the key, then binary search call low and mid minus 1. So its upper bound is mid minus 1. In this case, the lower bound is mid plus 1. If key is not present in this array, we return minus 1. Let's discuss with example. So here we have array with 9 elements. This array A with 9 elements 1, 5, 7, 8, 13, 19, 20, 23 and 29. All they are the sorted. So in this array, so find the location of the item 23 in the array. In first step, beginning is 0, end is 8, so mid is 4. So array of mid means A of 4 is equal to 13. So 13 is less than 23. Therefore, the element, the key value is in second half of this array. In this second half of this array. And this is on a second step. When we know the element is on second half of the array, we again calculate the beginning and mid. So beginning is mid plus 1, that is 5, end is 8, and mid is 13 divided by 2 is equal to 6. So A mid means A of 6 is 20. Now 20 again is less than 23. The key value is 23. Less than 23, that means the key value is on a second half of this mid value. So the element is here, our key value is. So in step 3, again we calculate the beginning, mid plus 1, that is 7, end is 8. So mid is 15 divided by 2 is equal to 7. So A mid means A of 7. A of 7 is 23 and it's the key value. Therefore, set the location of mid. So the location of the item will be 7. Time complexity for binary search. So here, let's say the iterations in binary search terminates after k iterations. At each iteration, the array is divided by half. So let's say the length of array at any iteration is n. At the iteration 1, the length of array is n. At the iteration 2, the length of array is n by 2. At the iteration 3, the length of array is n by 2 divided by 2. That means n divided by 2 raised power 2. That is n by 4. Therefore, after k iterations, length of array is n divided by 2 raised power k. After k division, the length of array become 1. Therefore, length of array n divided by 2 raised power k is equal to 1. That means n is equal to 2 raised power k. Now we apply the log on the both side. Here the log on the both side. Then we have log n base 2 equal to log 2 raised power k base 2. So log n base 2 is equal to k log 2 base 2. This log 2 base 2 is 1. So log n base 2 is equal to k. So hence the time complexity of binary search is log n base 2. Thank you. Hi, myself Dr. Vinder Kumar. Today in this session, we will discuss about the merge sort. If we can break a single problem into smaller sub-problems, solve the smaller sub-problem and combine their solutions to find the solution of the original big problem, it becomes easier to solve the whole problem. In merge sort follows the rule of divide and conquer. to sort a given set of numbers or elements recursively, hence consume less time. It works on top-down approach. Most implementation produce a stable sort. It is also a stable sort, which means the equal elements are ordered in the same order in the sorted list. In merge sort, the given unsorted array with n elements is divided into n sub-arrays, each having one element, because a single element is always sorted in itself. Then it's repeatedly merge these sub-arrays to produce a new sorted sub-array, and in the end, one complete sorted array is produced. Divide and conquer strategy. Using the divide and conquer technique, we divide a problem into sub-problems. When the solution of each sub-problem is ready, we combine the results from the sub-problems to solve the main problem. Suppose we had to sort an array A. A sub-problem would be to sort a subsection of this array starting at index P and ending at the index R, denoted as A of P R. In section divide, if Q is the halfway point between P and R, then we can split the subarray A of PR into two subarrays, A of PQ and A of Q plus 1 to R. In section conquer, in the conquer step, we try to sort both the subarrays A of PQ and A of Q plus 1 to R. If we have not yet reached the base case, we again divide these subarrays and try to sort them. In section combine, when the conquer step reaches the base step and we get two sorted subarray A of PQ and A of Q plus 1 to R, we combine the results of creating a sorted array A of PR from the two sorted subarrays A of P to Q and A of Q plus 1 to R. As we have already discussed, the merge sort utilize divide and conquer rule to break the problem into subproblems, the problem in this case being sorted a given array. In merge sort, we break the given array midway. For example, if the original array has 6 elements, then merge sort will break it down into two subarrays with 3 elements each. If the original array have odd numbers like 7 of elements, then merge sort will break it down into two subarrays with the first 3 elements and second have 4 elements. But breaking the original array into two smaller subarrays is not helping us to sorting the array. So we will break these subarrays into even smaller subarrays until we have multiple subarrays with single element in them. Like in this example, here we have initial given array with the 8 elements, and first we divide the 4 elements on left, 4 elements on right side, P to R, and then again it's P to R. So again we divide the 2 elements on left, 2 elements of right of this sub problem, and in this sub problem again 2, 2, and finally we reach on a single sub array or sub problems when P is equal to R. Now the idea here is that an array with a single element is already sorted. So once we break the original array into sub arrays which has only a single element, we have successfully broken down our problem into base problem, and then we have to merge all these sorted sub arrays step by step to form one single sorted array. In merge sort, we follow the following step. The step 1, we take a variable P and store the starting index of our array in this, and we take another variable R. Here the R, and store the last index of array in it. In step 2, then we find the middle of the array using the formula p plus r divided by 2 and mark the middle index as q, and break the array into two sub arrays from p to q and from q plus 1 to r. In step 3, then we divide these two sub arrays again, just like we divide our main array, and then continue like in this picture. Once we have divided the main array into sub array with single elements, then we start merging the sub arrays. So in this example, we have the elements array with the 8 elements 14, 7, 3, 12, 9, 11, 6 and 12. We have to pictorial representation how the merge sort will sort the given array. First we divide the complete array into two sub array. From 0 to 3 is the first sub array and 4 to 7 is the second sub array. In next iteration again we divide further left sub array 0 to 1 and 2 to 3 as shown in this figure, and finally we reach at the single element in each sub array. And in merging process we sort these array and merge them and finally get the sorted array at last step. So here the splitted array, the single element in each sub problem, then we sort this into this manner and then merge these into two elements in each sub array, and then again these 4 elements, the 2 elements in this array and 2 elements are in this array, and again we sort. First we check the 3 become in this array, then 7, the indexes increases in this array, and then 12, then 14, and same happen in this array, and finally we get the sorted array. So in implementation part of merge sort, the merge sort function repeatedly divide the array into two halves until we reach a stage where we try to perform merge sort on the sub array of size 1. That is, here we have condition p less than r or sometimes p equal to r. After that the merge function comes into play and combine the sorted array into larger array until the whole array is merged. To sort the entire array we need to call merge sort. This is initially we call the merge sort by array 0 and length of array minus 1. The merge sort algorithm recursively divide the array into halves until we reach the base case of the array with one element. So this is for the left merge sort and right merge sort. This divide the left side and this the right side, and then this is for combine part. After that the merge function pick up two sorted sub arrays and merge them to gradually sort the entire array. The most important part of merge sort algorithm is merge step. The merge step is solution of the simple problem of merging two sorted list or a array to build one large sorted array with 3 steps. First we compare the current element of the both arrays, copy the smaller array into the new array or on a sorted array, move the pointer element containing smaller element, and then again repeat this step until we combine the whole array like this, A of PR. And by analyzing the merge sort, complexity analysis of merge sort is quite fast and has a time complexity of O n log n. In this section, we will understand why the running time of merge sort is O n log n. As we have already learned in binary search that whenever we divide a number into halves in every step, it can be represented using a logarithmic function which is log n base 2, and the number of steps can be represented by log n plus 1 at most. Also, we perform a single step operation to find out the middle of any subarray, that is of 1, and to merge the subarray made by the dividing the original array of n elements. A running time of O of n will be required. Hence, the total time of merge sort function will become n log n plus 1, which gives a time complexity of in term of O n log n base 2. Thank you. Hi, myself Dr. Vinder Kumar. Today in this session, we will discuss about the quicksort. The quicksort is also based on the concept of divide and conquer, just like merge sort. But in the quicksort, all the major work is done while dividing the array into sub-arrays. While in case of merge sort, all the real work happened during the merging the sub-arrays. It is also called partition exchange sort. After selecting an element as pivot element can be any element from the array. It can be the first element or the last element or any random element. Here in our case, we will take the rightmost element or the last element as pivot. So here in quicksort, following are the steps involved in quicksort algorithm. In quicksort, we call this partitioning. We divide the array for the first time. It is not simple breakdown of array into two subarrays, but in case of partitioning, the array elements are so partitioned that all the elements smaller the pivot will be on the left side of the pivot, and all the elements greater the pivot will be on the right side of it, and the pivot element will be at its final sorted position. The elements to the left and right may not be sorted. Then we pick the subarrays, elements on the left of pivot and the elements on the right of pivot, and we perform partitioning on them by choosing a pivot in the subarrays. So in quicksort algorithm, we have two functions. One is quicksort, second is partitioning. In quicksort algorithm, we have major 4 steps. First is make the rightmost index value as a pivot. Step 2, partitioning the array using pivot value. Third is calling the quicksort for the left partition recursively. Step 4, quicksort right partition recursively. And in partition function, we have 7 steps. Step 1, choose the highest index value as pivot. Take two variables I and j, point to the low index of an array. This is the I and this is the j variable. And then for loop in step 3, traverse all the elements from low to high except pivot. The step 4 and 5 are come under the step 3 in a for loop. If the current element of jth location is smaller the pivot, then increment in I and swap the ith with the jth element. After the completion of this for loop, the swap the next to ith with the jth element. In step 7, return the next to ith element location that is acted as a pivot element, this I plus 1. So here we have example of quicksort algorithm. Here we have array with the 7 elements. These are 5, 9, 25, 100, 35, 45, 80 with the indexes 0 to 6. So initial set low is equal to 0, high is equal to 6 and pivot is equal to 80. This is the last element of our array. So we move j from low to high minus 1 means 0 to 5. So initial j is equal to 0, I is equal to 0. The jth element is less than equal to pivot. Yes. Then increment in I and swap ith element with the jth element. Both are pointing to the same element, so no change. Then j is equal to 1, I is equal to 1. Now jth element is greater than pivot, no change in I and any exchange. So again j is equal to 2, I is equal to 1. Now jth element is less than pivot, then again increment in I and swap the ith element with the jth element. That means 90 and 20 are swapped with each other. Then j is equal to 3, I is equal to 2. Now the jth element is greater than the pivot, no change in I and any element in array. So j is equal to 4 and I is equal to 2. Now jth element is less than the pivot, then increment in I and swap ith element with the jth element. So 35 is swapped with the 90. Now j is equal to 5, I is equal to 3. Jth element is less than equal to pivot, again increment in I and swap ith element with the jth element. 45 is swapped with 100. So now we have this array, and after the completion of this loop, now j point to the next element, that is high. So finally place pivot at the correct position by the swapping I plus 1 with the array of high, that is pivot, means 80 swapped with the 90. So after this, now 80 is at its correct position. Hence after the first pass, pivot 80 will be set at its position with all the elements smaller to it on its left and all the elements larger than to it right. Now 5, 25, 35 and 45, these become in a one sub-array, and 190 are in another sub-array, are considered as a two separate sub-arrays, and same recursive logic will be applied on them, and we will keep doing this until the complete array is sorted. The quicksort is based on the divide and conquer algorithm. Quicksort to provide an average case performance that usually outperforms other sorting algorithms. The advantage of this quicksort is that we can sort in place, that is without the need for a temporary buffer depending on the size of the inputs. Quicksort partitions an array and then call itself recursively twice to sort the two resulting subarrays. This algorithm is quite efficient for large size data sets, as its average and worst case complexity are O n log n base 2 and O n square respectively. Thank you.